Alright, welcome back guys to the finite element methods. So in the previous meeting we have looked at how we can derive the element stiffness metric from this internal strain energy equations, and for now in this part 2 we are going to look at how we can deal with the potential energy, especially contributed from these distributed loads, which is given by P in this potential energy equation. So in the previous meetings we have look at the three loadings that contributed to these beams studies. The first one is known as the distributed loads. So the distributed loads, which is in our discussion is labeled by P, will consider to act along length of elements. So we have our element from nodes number 1 and nodes number 2. So we will consider that the distributed load will be spanning all over these beam elements. And in this finite elements, it is not convenient to solve these elements, the distributed load as it is, but somehow we have to consider to transform this distributed load into equivalence force and moment that acting on these nodal points. So let's first look at this potential energy due to the distributed load as obtained from the potential energy equation, which is given by the integrations all over the length element. So we integrate from nodes number 1 until nodes number 2. We do the integrations, then we integrate the distributed load P, and then multiply by its a deformation field and multiply by distance dx. So in this case we as we discussed in the previous meeting, the V is actually contributed from H multiplied by Q, which is H here is the Hermite functions and Q is the deformation, the translation and the rotations at nodes 1 and nodes 2 for this in this element number number 1, for example. Then as always it is not convenient to work in the Cartesian coordinate system, then somehow we have to find a way to convert it into the the natural coordinate systems. So substituting the V, which is H multiplied by Q, and dx into this potential energy equation give us these equations, which is, as we can see now, this equation is now written in the natural coordinate systems. So, and again here if we substitute for the H and rearranging the equations, this equation, then we will get a new expression for this potential energy equation as a functions of Hermite function, and also which is written, everything is written in the natural coordinate systems. And furthermore, if we expand the Hermite functions terms hi in the previous slide, then we integrate every term with respect to the natural coordinate system, then we finally get the first equation in the slide, which is we can write this equation in more compact equations in the metric form as given by the second equation here, where the f here actually contains all of the coefficients that contain in this square brackets. So actually this equation is actually developed for a distributed load that have the directions in the upwards directions. So, and of course in engineering problem we may face distributed load that pointing in the downward directions. So in this case, then the equation here is not valid. So this equation is only valid for the distributed load that is pointing in the upwards directions. So let's look at the physical interpretations of the equation that we developed just now. So this equation that we have at the bottom here is the equivalence nodal force and moment, which is we transform it from this a uniform distributed load that's spanning all over our beam element from the nodes number 1 until nodes number 2. So if we consider this beam which is subjected to the uniform distributed load, which is represented by P, then physically if we can imagine, if for example if I put fixed boundary conditions, then we can imagine that the beam which is at the rest, which is may look something like this, but after we apply this distributed load, then the beam will somehow deform in this shape. So this is the initial, so this is the deformed beam. So as we can see here, there is the deformed beam has the maximum deformation somewhere in the middle of this of the beam element, and the way it deformed here is something like there is a moment that pushing the structure to form that shapes. And of course here, since we have this of the distributed load that is pushing the structure in upward direction, so we can replace this as well with a point load that pointing upward at both nodal point, node 1 and node 2. So this is the physical thing that happens on one beam element subjected to a uniform distributed load. But somehow positive conventions must be imposed to make the finite element analysis to be easy to be constructed and solved. So taking that the upward directions and anti-clockwise direction as the positive directions in our considerations. So and we try to match these sign conventions with the one that we developed here. So this one we have positive sign convention, which is we have the same direction. This one which is also in the anti-clockwise direction. On the nodes number 2 we have the vertical force in the positive direction, but as we look at this, the moment at this moment at nodes number 2, which is in the opposite directions from this the positive sign convention that we agreed. So this is will be give us the negative value of the moment that apply at nodes number 2. So this is what is happening in this equation. So PL over 2, which is actually refers to the equivalence nodal loads, nodal force that applied to the nodes number 1, which is contributed from this uniform distributed loads. And the same applied here at nodes number 2, where we still have PL over 2 as well. So if we look at the row vectors, our row vectors, we have PL E over 2 and PL square over 2, which is refers to what is happening at nodes number 1 here, and PL over 2 and PL square over 12, which is referred to what is happening at nodes number 2. So as I mentioned just now, negative here is actually to make the rotation that we have at nodes number 2 to match with our positive sign conventions. But what will be happens if we have the distributed load that is pointing in the downward directions? So if, for example, now we have the beam which is subjected to uniform distributed load and it is pointing downwards, so we can draw this the equivalence nodal force and moment applied to this nodes number 1 of our structures and nodes number 2 of our structures, so that it has so now let's reconsider a beam elements which is subjected to a uniform distributed load that is pointing downward. So from there we can expect that this beam here, which is at the rest, initially at the rest, then it will deform to form this bending that is somehow it's like moving in the downward directions, and to and this also actually can be viewed that there is something like we have a moment that pushing the structure so that it bends that way. And since we have this uniform distributed load that pointing downwards, so we can replace it or substitute it with a point load that is pointing downward as well at both nodes 1 and node 2, which is the magnitude of these loads, which is PL over 2, and then we have PL square over 12 for the moment. Then we have PL over 2 for the point load, and then we have PL square over 12 as well for the moment. But in this case, this is the physical thing that is happening to our structure. And again here we have to match these the equivalence and the force and moment that we generate with these the positive sign conventions that we have here. So since we have this the point load that is pointing downward, then we try to make it we change its directions to match the our positive sign convention, then we actually can simply put negative to our equation. So negative there, we put negative here, and then we check the rotations. So at nodes number 2 we have rotation which is following clockwise directions. On the other hand, we should have it in the anti-clockwise direction, so we put it negative there. And the rotation at nodes number 2, which is following our positive sign convention, then we have positive PL square over 2 for the rotation at nodes number 2. So to write the equivalence nodal force and moment vector for this kind of distributed loads here, then we will have our FE here, which is will have PL over 2 negative, then we have negative as well, then at the nodes number 2 we have negative PL over 2, and then for the rotation we have PL square over 12. So all of this is written in the transpose. We transpose everything here. So the first equation here again is actually developed for the uniform distributed load that is that have the upwards force directions, and the second equation that we have here is actually developed for the uniform distributed load that having the downwards force directions. Alright, at this stage actually we should be able to set up our system of linear equation in the form of K Q equal to F. Okay, K is actually refers to the global system of element stiffness metric. Q, which is the our unknown, which is the unknown variable that we would like to predict, and F, which is the column vectors that contains force vectors. So when we have this done and assembled to represent the whole structure that we want to solve, then we can now predict the Q, and this information can now be used in calculating the shear force and also bending moments. Bending moments, which is represented by M at any point along the beam elements, is given by equation number 1, which is M equal to EI multiplied by the second derivative of V over X, where V here is just the deformation field and is given by H multiplied by Q, where we have done in the previous meetings, the terms the second derivative of V over X, which is can also be written in the natural coordinate system, which is given by 4L square multiplied by the second derivative of V over Z square. And this also actually can be represented by the second and the third equation in these slides. Substituting equation 2 into equation number 1 then simply give us these first equations in this slide, which is, as we can see here, for the bending moment, it can predict by using this equation that requires the modulus of elasticity and second moment of inertia, and also the length of elements considered. And at the same point here, we also require the informations at each node point in terms of the vertical displacement and rotations, and also the displacement and rotation at nodes number 2. Shear force V at any point along the beam elements now is given by the gradients of bending moments along the elements that we consider, and this is actually equivalent to the EI multiplied by the third derivative of V over X. And again here we know that the V here is actually the deformation field, which is given by H multiplied by Q, and converting the V over the X cube from the Cartesian coordinate system into the natural coordinate system give us these equations, and this is also equivalent to the equation number 4, which is contained Q1 to Q3n and Q4. Substituting this equation number 3 into equation number 4 into equation number 3, then give us the expression for the shear force within our beam element considered, which is given by this fifth element in our slide here. Alright, now let's look at our first example of beam structure subjected to distributed slope and simply supported as shown here. So for a beam with the loading shown below, determine the slope at nodes 2 and nodes 3, and B, the vertical deflection at midpoint of sections 2, 3, so it is somewhere there. So we have the beam which is 2 meter length, which is given its modulus of elasticity, which is 200 gigapascal. The moment of second moment of inertia, which is 4 times 10 to the power of 6 millimeter to the power of 4, and this structure is simply supported with a fixed point at nodes number 1, then at nodes number 2, or 1 meter from the left hand side. So the beam is supported with this pin roller, and we have another pin roller at the nodes number 3, or the most right end of this beam. So if this kind of this problem can be actually solved by simply taking 2 elements. So this beam can be divided into 2 elements, which is the element number 1 and the element number 2. and we can start label the nodes numbering, which is node number 1, which is located there, nodes number 2 there, and nodes number 3, which is located somewhere there. So for the element number 1, there is no loop applied there, so we can skip this part. But for the element number 2, we have this a uniform distributed load of 12 kilonewton per meter acting all over these elements number 2. So if we can remember that if this uniform distributed load must be represented by the equivalence nodal force and moment, which is if we draw in its positive sign convention to have something like this, where its magnitude is PL over 2 and PL over 2 here as well. But in terms of these directions, we have opposite direction, so I give it negative there and there, and we have PL square over 12 . So here will be negative, and here we have positive PL over square, PL over 12. So we know the length of these elements, L equal to 1 and P equal to 12 kilonewton per meter, and if we substitute this value in our equation there and there, then we can obtain this value here, which is given by 600 newtons and 1000 newton for the displacements and rotations, displacement and rotations, and nodes number 3 as well. So we have to set up the system of linear equation, which is in the form of KQ equal to F for our structure. Then for each element, then we have to calculate or prepare this element stiffness metric, which is given by this equation, and it must be applied for each element. So considering the element stiffness metric equations, then we solve for each element, K for element number 1 and K for element number 2, which is given by these two metrics, the square metric of 4 by 4. So it is a convenience to write the address on the on this part of the metric as well, so that it will be easy for us to transfer this metric or to build the to assemble this matrix later. So I write everything on the top and on the side of this matrix. But we can see from these two matrices there are several elements in the matrix, which is these 4 elements, which is reside in the row 3 and column 3 and 4 and column 3 and 4 in K1, and row and column 3 and 4 in K2. They are actually sharing the same address here. So the K global which is the summations between k1 and k2. Since we have two elements, so we add both k according to its address. So since we have three nodal point, and we know that for each nodal point we have 2 degrees of freedom, then we can expect that for the whole structure we will have maximum 6 by 6 square matrix in our element stiffness matrix. Thus, adding the K1 and K2 give us this matrix here, where as we can see, so if I can label again here, the index, or we can call this as address as well. So the value here, which is obtained from the two matrix that we developed just now for each element. So for the element that is not exist in its relations here, for example column 5 and row number 1, which is does not exist in our elements matrix, then we just can simply replace this value by zeros values. So the equivalence nodal force and moments will carry the same value as calculated before in the previous slide, but will carry the negative sign here, which is to match with the positive sign conventions as we agreed before. For the global force vector, is must be added together as well. So the global force vector that we have here is actually the summations of the force that exist at all nodal points in our structures. So the first two forces, which is equal to 0 here, because of no applied force acting at nodes number 1 here, but we have the equivalent force and moment at nodes number 2 and nodes number 3, which is contributed from these distributed loads. When we have assembled our element stiffness matrix to form a global element stiffness matrix and the global load vectors that resemble complete systems of the structures to be analyzed, so we can rewrite all of this in the system of a linear equation, but in this case we write this in the matrix form, which is this is our K matrix, and this is our unknown, and this is our force vectors. So at this stage it is very important to go back to our problem and identify all the boundary conditions imposed to our systems. So at node number 1 is where our structure is fixed to the into the wall. So we can expect at this particular point there will be no translations or rotations occur at this nodal point. At node number 2, which is where the structure is supported by a pin roller, that means the translation here, if we take the Q here, will be equal to 0, and the pin actually will allow the rotation to occur at this particular point. So we may have translations in this direction, but we are not interested in the translations in the horizontal directions. We just interested in the vertical direction. So Q will be equal to 0. This Q will have value. This Q will be equal to 0, and this Q equal to 0 as well. So if I can put the index, I have index 1, 2, Q3, Q4, Q5, which is again we have pin roller, and this is equal to 0, and then we expect, due to the pin support here, Q6 will have some value as well. So Q1, Q2, Q3, 5 and 5, due to the boundary conditions, that will have a 0 values. So coming back to the system of linear equations, where we have Q1, Q2, Q3, and Q5, which is all of these are equal to 0. So this full system of linear equation actually can be written in the reduced system of linear equations by considering these knowns displacement due to the its boundary conditions. So for the knowns displacements, Q1, Q2, 3 and 5, which is equal to 0, and to write a reduced system of linear equation, then we can eliminate the whole row and the whole rows 1, 2, 3 and 5, and the whole column 1, 2, 3 and 5 as well. So by doing this approach, we can simplify our system of linear equation, which initially we have a 6 by 6 square matrix. Now we have reduced it into 2 by 2 metric systems. So now we have able to reduce a big system into the simplified system of linear equations by imposing boundary conditions. Now at this stage, we can actually solve this system of linear equations using the calculator. Then we found that the displacement at nodes number 4 and number 5, which is actually representing the rotation, and this is equals to these two values and in unit radians. In the second equation, we are asked to predict the vertical deflection at the midpoint of the sections 2, 3. So this is our section 2, 3, and we would like to determine what is happening at the midpoint of this element. So the field displacement or deformation at the midpoint within element number 2 and within the nodes 2 and 3 can be obtained by solving this interpolations equations. Knowing that for one element, the value of z on the left hand side, which is equal to 1, and alright, knowing that the value of natural coordinate system for one prime element, which is z equal to -1 on the left hand side and z equal to +1 on the right hand side of our element, then at the midpoint the value of z, which is equal to 0. So substituting this z equal to 0 into the Hermite shape functions for the h1, h2, h3 and h4, then we obtain that h1, which is equal to half, h2 equal to 1/4, h3 equal to half, and h4 equal to -1/4. So from the calculated displacement, which is obtained from the system of linear equation that we solved just now, then for element number 2, where we have to consider these 4 values to be substituted in these interpolation equations. So for the field deformation at z equal to 0, which is occur at the midpoint of our elements, and substituting the h1, h2, h3 and h4 with all these values, and substituting q1, q2, q3 and q4 by these values, which is obtained from the system of linear equations, then we actually can determine that the field displacement at node number 0, which is equal to -8.93 times to 10 power to -5 meters.